Our aim is to talk about a theorem called the fundamental theorem of finitely generated abelian groups. So first I have to explain what finitely generated group is. So a group is finitely generated if there exists a finite number of elements, G1, G2, up to GR, these are elements of our group G, such that G equals the subgroup, denoted like so, G1, G2 with these brackets that is generated by the GIs. So here's what that means. This subgroup here, G1, the subgroup generated by G1, G2 up to GR, is the set of products of the GIs and their inverses. So a typical example of an element in this subgroup might be G2 times G1 inverse times G2 to the -3, for example. This product here is G2 times G2 times G1 inverse times G2 inverse times G2 inverse times G2 inverse 3 consecutive times. So that's what I mean by this set here is products of the GIs and their inverses. So let's look at some examples. Well, all cyclic groups, such as the integers and Z mod n, are finitely generated. In fact, they're generated by a single element. So this definition here might be reminiscent of the definition of a cyclic group. That's where there's a single generator. Secondly, finite direct products of cyclic groups are finitely generated. So for example, Z is cyclic, Z4 is cyclic, and we take the direct product, or sometimes I just call it product, and so get this group Z cross Z4. And again, this consists of ordered pairs, like 5, 2, where the first number, in this case 5, is an integer, and the second number is an integers between 0, 1, 2, and 3 inclusive, coming from an element in Z4. And I claim that this group is generated by 1, 0 and 0, 1. It can be generated by other elements as well, but at least it's generated by these two elements. Why? Well, let's take an arbitrary element, 5, 2, for example, in here. I want to write it as some combination of these two elements. Well, I can take 1, 0 and take its inverse, which is -1, 0, and multiply that 5 times. Or because I'm talking about an additive group or abelian group, we use addition. And so that's the same as multiplying by -5. And then 2 copies of 0, 1 will give the 2 there. So this is what you would write if you wrote things additively, which is what we'll usually do when we're talking about groups like abelian groups like so. If you were using this multiplicative notation up here, which is an unusual thing to do, but this would be 1, 0 to the -5 times 0, 1 squared. But no one ever writes this. Now, all finite groups are finitely generated. That's another set of examples. And that's because we can simply take all the elements of the group as the set generating the group. Okay, let's do some non-examples. In other words, groups that are not finitely generated. One example is the rational numbers with the group operation of addition. This is not a finitely generated group because, and it turns out the reason is that there are infinitely many prime numbers. And if you did have somehow a finite set of generators, those generators will generate fractions with only a finite set of primes dividing the denominators. So for example, suppose 1/2 and 1/3 generated for some reason this group Q of rational numbers. It doesn't, but suppose they did. Well, what does the group generated by 1/2 and 1/3 look like? When you add any number of copies of 1/2 to 1/3, you'll only get numbers that have 6 in the denominator. You won't get anything that has, for example, a 5 or a 7 in the denominator. Another example is the group of polynomials with integer coefficients. So that's this notation here. Polynomials in X, and the group operation is addition. And this is not a finitely generated group because the polynomials or terms in here have degrees that are arbitrarily large. And if you have a finite set of generators, well, or any finite set of polynomials, the group that they generate has only polynomials of degree, the largest degree in your set of generators.